Start recording. All right. So, are there any questions about probability, discrete probability, discrete probabilities, the binomial distribution? So, any questions about that? Hmm? That's proof. That's proof by induction. The turtle shell or the turtles is about proof by induction. Yeah, the base case versus the induction step. So, any questions about those things? And any questions about the binomial distribution? No questions about the binomial distribution? How about applications of the binomial distribution? Okay, so that would be kind of useful, right? Because, why do we have to study this? What does it have anything to do with your future career as a computer science or computer engineering major? Okay. Okay. So let's say you are responsible to develop um, like an online game engine, okay? So with an online game engine, you are responsible to design a protocol so that the game client and the game server can communicate. Now, most of the time, we do not use TCP IP connections with games anymore. Instead, we use UDP. The difference between TCP versus UDP is TCP is what we call a stream-based, fully handshaken type of protocol where the order of you transmitting bytes on one end is guaranteed on the other side to be received in that order. Okay, so that's TCP. UDP, on the other hand, does not guarantee the correct ordering of transmitting and receiving can be out of order, and there's no guarantee of reception either. In other words, if the transmitter, the sender, does not check and say and have its own logic of checking whether the receiver has received a particular packet, there's no way can tell. Whereas TCP is guaranteeing it because the protocol itself has built-in mechanisms to guarantee the reception of the data. Okay? Yep. Yes, it's a speed trade-off because TCP has quite a bit of overhead associated with it, and also ties up a connection, quote unquote, a conceptual connection whenever you want to transmit something. Whereas UDP is completely like, okay, here's a packet, okay, but if I send 3 packets, A, B, and C, are they receiving in the order of A, B, and C? Who knows? You might receive C and then A, but where's B? It went missing, gone. Okay, so unless your own gaming protocol has ways of checking that, timing out, checking, okay, something doesn't make sense, check on the other side. UDP itself is really simple to implement. It's very fast, but it also put all the burden of making sure that your transmission is okay on you as the game, in this context, the game developer. Okay, so but what we're interested in here is what are the chances that something is transmitted incorrectly. Okay, all right, and that part is actually not part of UDP's responsibility. But let's say you're moving one level lower, you're dealing with like fiber optic, or you're dealing with radio frequency technology. So you're actually working with a raw data bits. So we'll talk about a 1024-bit packet. Okay, this is actually one of the exam questions. Um, and let's just say that by observing your circuitry, okay, you know that the chances of transmitting a bit correctly is p. Okay, so p can be any number from 0 practically to 1. Okay, if it's 0, that means why are you using it? If it is actually 0, it's actually nice in a way because it means that every single time you transmit a 0, it is received as a 1, and every time you transmit a 1, it is received as 0. So it is actually useful. The worst case scenario is p equals to 0.5. Then you really have no idea of what you transmitted. Okay? So that means the chances of transmitting a bit incorrectly is 1 minus p. Okay, it really is just the flip side of that. Are we doing okay so far with this? All right, cool. So let me ask you this question, okay? So the question is, what are the chances that there is one error bit in a 1024-bit packet? Okay, so that's the question. I don't really care whether it's the first bit or the last bit or any bit in between. I'm just asking, what are the chances that there's one single error bit in a 1024-bit packet? So we already know, what is P, which is a bit transmitted correctly, and what is 1 minus P. We'll call it Q, okay, just so that I don't have to keep saying 1 minus P. So now we have P and Q. So how would you answer this question? And by the way, I'm using this as an example to illustrate the application of the binomial theorem. So it has something to do with binomials. Okay, so let's go ahead and start with something that has to be true. Okay, P plus Q to the power of 1024 is 1. Does that make sense to you? Because Q is by definition 1 minus P, so P plus 1 minus P is just 1. 1 to the power of 1024 is 1. Okay, so we kind of know that already. But that covers all the possible ways of having erroneous bits. Okay, so let's break this up a little bit, and we'll just break out the first item and the last item first. The first item is P to the power of 1024 times Q, okay, times Q to the power of 0, right? So if you expand out, okay, P plus Q times P plus Q times P plus Q 1,024 times, and you say, what is the term that has P to the power of 1024 and Q to the power of 0? There's one of them. That makes perfect sense, right? The last one also makes sense, and it's easy to work with. The last one is just P to the power of 0 times Q to the power of 1024, and there's also just one of them. Okay? So what we're interested in is, what about the second one? Okay? What do you think the second one's going to look like?
24 times Q to the 23.
Yep.
Q to the 1.
So the second term is, okay, I'm just going to insert it here. The second term is we have 1024 as a constant, the number of times P to the power of 1023 times Q to the power of 1. I want to emphasize to the power of 1 here, because we want to make sure that the power of P and the power of Q add up to 1024. Okay? This number turns out to be 1024 because it's kind of easy to kind of imagine that, because we are just trying to figure out how many ways can we miss 1P. And you can basically, quote unquote, miss 1P by missing the first one, the second one, the third one, and so on. So there are exactly 1,024 ways to miss the first P. Okay? That's one way to look at it. So that kind of answers the original question. Okay? What are the chances there's exactly one error bit in 1024-bit in a 1024-bit packet? So what if I were to ask you this question? Yep, go ahead.
So when you're asking for the chances that there's one error bit, is that like the number of possibilities or the probability?
It's the probability.
So
This is the actual probability of having exactly one error bit in 1024.
that number over like 2 to the 1024? Or
Say that one more time.
would you put that number then like 1024 divided by 2 to the 1024 times?
Nope, you don't have to divide anymore. So if you pull out this number, that by itself is the probability. Yeah, that thing is the probability. And it is one term of the entire sum, which adds up to 1, which represents all the possibilities of transmitting 1024 bits. Okay, so what we want to do now is to say, what if we want to generalize and say that we want k error bits in a 1024-bit packet? In other words, I might want to add up, what if I want to deal with 1, 2, 3, and 4 error bits in 1024 bits. Okay. So what do you think that's going to look like? Do you guys remember the binomial theorem? In other words, I'm looking for the constant that I need to multiply to p to the power of 1024 minus k times q to the power of k. So we know this part, what this part means, right? Because we have k bits that are erroneous. So p to the power of 1024 minus k takes care of the bits that are transmitted correctly. And then, hold on just a second. And then q to the power of k takes care of the bits that are transmitted incorrectly. Yes, go ahead. Say that one more time. Nope, it is not 1024 times k. This has to do with something that we talked about. Yeah, go ahead. It's choose exactly, which is also known as combination. So it's 1024 choose k in this case. I use the word combin, not because I'm too lazy to type out combination, but this is the actual name of the formula that you can use in a spreadsheet. So that makes it very handy because now you can just plug in, these things, have k being the first item of the first column, and then you can have a table to show you how these numbers stack up, depending on how you want to program in the p and the q. Okay, so it has practical, use because so now the question is, how do we know about P and Q? How do we know about the chances of transmitting one single bit correctly? That's done by, you can do it by observation. This is usually done empirically. So basically you build a circuit, you transmit a gazillion bits, okay? And then you just count how many bits are transmitted incorrectly. So, or in this case, correctly. So that will give you the actual number for P. But once you have the number for P, you can use all this math or binomial theorem to figure out if your packet has 1024 bits, what are the chances that you can have 1 bit of error, 2 bits of error, 3 bits of error, and so on. Okay, so just by looking at this, if I tell you that P is kind of close to 1, okay, let's call it 99.9%, okay? How would the chances of having 1 error bit compare to the chances of having 2 error bits? Which one do you think is going to be bigger? The chances of having 1 error bit or the chances of having 2 error bits when P itself is 99.9? Huh?
Is it one or at least one? What are the chances of having one error bit exactly or at least one?
Exactly 1 versus exactly 2. Okay, so basically what we are looking at now is the first one is 1024 choose 1 times p to the power of 1023 q times q. Oh, sorry. Yep, I got it right. Okay. And then the second one is combin 1024 2 times p to the power of 1022, sorry, times q to the power of 2. So the question is, how do these two numbers compare? What do you think? So do you still remember combination? How that relates to factorial? So 1024 choose 2 is 1024, sorry? Okay, it's the factorial. It has to do with factorial. So what is 1024 choose 2? It's 1024 factorial divided by 1022 factorial times 2 factorial. Okay? So it's basically, compared to the first one, the denominator is off by about 1,000. Is that okay? So when you look at combin 1024 2, it is about 1,000 more than 1024 choose 1. Is that okay? But then we have this part being not the same. p is really close to 1, so we'll just kind of say that, off by 1 is not going to make much difference in terms of p to the power of 1023 as opposed to p to the power of 1022. We'll call that, yeah, it's going to wash, but no big deal. But q is not, right? Q is, if I say 99.9%, q is basically 0.1% or 1,000th, of something. So the second one, even though combin 1024-2 is about 1,000 more, but q square is also 1,000th of just q itself. So they wash out for the most part. Okay, I would say, because this one is close to 24, so I would say the second one is slightly larger than the first. Not by a whole lot, it's going to be slightly larger. Does that make sense? So the chances of having exactly one error bit is about the same as the chances of having 2 error bits when p is 99.9% or 0.999. Okay? So what is going to tip the scale? Okay, if I want to tip the scale and say the chances of having exactly 1 error is going to be greater than the chances of having 2 errors, what do you think is going to change? And how do we change that? Combin 1024-1 versus combin 1024-2 is going to be the same, right? They're going to be off by about 1,000 times. So what we can change is p versus q. So if p is a higher chance, if p is 99.999% of a chance, then q is going to be a lot smaller. So q is not 1,000th anymore. It can be a lot smaller. So that means the second number, even though the combin part is about 1,000 more, but if q is a lot less than 1,000th, then the second number is going to be smaller. Is that okay? So at some point, okay, when you look at the chances of having 3 error bits, the chances of having 4 error bits, and so on, at some point, it becomes so small of a number, they can just go like, okay, it is inconsequential. We don't have to consider that anymore because it's just by scaling, it does not compare to the chances of having 1 or 2 error bits. Is that okay? But this gives you the ability to kind of guesstimate the total probability of having at least 1 error bit in the packet. Yep.
Is it possible to a way to check which error bits would be the
It is not built into this particular problem because this problem is only saying that we have 1 error bit. It can be any one of the 1024 bits. If we say 2 error bits, it can be any 2 of the 1024 error bits. Excuse me, any of the 1024 bits in the packet. So we cannot locate which bit is transmitted erroneously. We just know that at least 1 bit is transmitted erroneously. Yep.
Would you accept that as an answer, or do we have to write it out as a definition?
So if this were an actual exam question, then I need you to show me how you got this. Why did you choose combination? And why did you choose these numbers here? Now obviously these all come from the binomial theorem, but why did you choose the binomial theorem? Because it has to do with the probabilities, the p plus q. Okay, each bit is p plus q. Okay, so when you transmit 2 bits, it becomes p plus q times p plus q. When you transmit 3 bits, it becomes p plus q times p plus q times p plus q. But what you're trying to look at is, I just want to know the chances of having 2 correct bits and 1 incorrect bit. So you're talking about p squared q, but the multiplier to p squared q is the combination. So you have to kind of explain your rationale of using the binomial theorem to do the calculation. Yep.
I did have a second question regarding to a package being sent.
Yeah, go ahead.
We know that there's going to be at least 1 error bit. How do you make up for having a difference?
Okay, so in a transmission in a hardware sense, what you can just report back if there's a report back mechanism. You just say that, okay, this packet is not received correctly. You don't even have to identify which bit is not received correctly. You can just say that it's not received correctly, and then the transmitter can try to retransmit. It depends on how slow it is to transmit the bits, but typically the checksum mechanism cannot tell you which bit is transmitted incorrectly. But that brings up another question of how do you know that one bit is transmitted incorrectly? So now you have to go into checksum mechanisms, and there are different checksum mechanisms. The most typical checksum mechanism is called exclusive OR. So let's say you're transmitting bytes, okay? You just take the exclusive or bitwise exclusive OR of all the bits, and you attach it as one quote-unquote checksum bit or checksum byte at the end of the entire packet. So you receive the 1024 bytes or whatever number of bytes. You do the exclusive between all of those, and then you check against the checksum. But that is a not very secure way to do things, because if two bits are incorrectly and they're the same position, then the checksum won't show that that your packet is incorrect. So that's why people use CRC. I cannot even remember the full name of CRC checksum. So CRC checksum is actually it's called cyclic redundancy check, but it's a checksum mechanism, and it can locate bit errors, even if it's on the same bit of multiple bytes, it will still be detectable. So it can detect a lot more problems than just exclusive OR. Yep.
How these software tools are actually developed
To
to like check stuff like bit correctness and for bit errors and stuff?
but CRC is one. If you want something that is even more has a higher chance of catching something, you can use MD5. Any type of the hashing, quote unquote, hash mechanism can be used as a checksum.
I'm talking about like how they're made.
Huh?
Oh no, I'm talking about the tools. How are the tools made? Like how they come up to develop the tools to do this?
How did it come up with the mechanism? That I do not know. So you can probably read up the history of CRC to start with, because CRC has been around for a long time. This is what people used when they still used modems. So when you use modems, they had transmission protocols called X modem, Y modem, and Z modem, and I think they all use CRC as a checksum mechanism.
Hey, what you call this? It was a hash.
It's basically a function on a stream. Okay, so in addition to CRC checksum, you can use Md5 hash. Okay, they call it a hash, but it really is kind of a checksum too. And then there's SHA1, SHA2, SHA1, SHA2. Those are also hash functions. So basically what a hash function does is you basically compute a single value that is really long, then kind of wide, out of a stream of bytes. Okay, and then the idea is it is very unlikely that two streams of different bytes will give you the same hash value. And that's how you catch, that you have a transmission error. So those are, kind of, the stuff that people used in the past to do this sort of thing. All right, but getting back to the problem that we are, trying to illustrate, are there any questions about this particular problem? What about the other way? What if I tell you that the chances of getting a bit transmitted correctly is only 90%? Then the chances of having two error bits is actually higher
Oh wait.
than having one error bit.
Oh my goodness. I thought it was gonna be like 10% because they matter.
Because the difference between these two, the combines, is only 1,000-fold. Okay, but when you look at Q versus Q squared, Q is only 0.1. Q squared is only 0.01. The 0.01, the 0.1 cannot make up for the 1,000th of magnitude change for the combination. So the chances of having two error bits is significantly higher than the chances of having one single bit when P is only 0.9. When P is 0.999, it's almost break even between having one versus two error bits. When P is 0.999999, then the chances of having one error bit is higher than the chances of having two error bits. But do you see how p itself can tilt the scale and change the shape of the curve? You can play with these with a spreadsheet, okay? And I highly encourage those of you who know and want to use a spreadsheet to just play it out, okay? Make a spreadsheet, make P a particular cell so they can change one cell and then it changes the entire spreadsheet, and then have the spreadsheet to plot out the curve as well. So that way you can look at the curve and go like, oh, so this is how we can change P and then change the shape of the curve. What do you think the curve would look like when P is about 0.5? If you plot out the curve, okay, just look at the shape. What do you think that's going to look like? Sorry? Do that one more time. I wasn't paying attention. Nope. When P is 0.5, then the chances of having it will be almost like a normal distribution. Exactly. It's almost like a pixelized version of the normal curve. That is the other reason why binomial distribution is significant, because this is how we approach the normal distribution. It just works out math-wise. How many people don't know what I'm talking about when I said the normal distribution? The bell curve, exactly. And how do we use the bell curve? I know this is out of context of this class because it's not discrete math anymore. But why do we care about the bell curve? It has to do with probability and statistics. But why is it important? Why is it even important to computer science people? It's out of the context of this class, but it is nonetheless worth mentioning. Okay, this is the bell curve. Okay, and how do we apply the bell curve? When do we use the bell curve? When do we use the normal distribution? When we want to find out. Okay, so if you want to know the true average of the population, but you can only have samples, right? Then the normal distribution will tell you how likely the actual population or average is given the average of your sample. Okay? Okay, I'll give you one context. Okay, so let's say I want to find out what is the average height of people. Okay, specific to ARC. Okay, so we are not even talking about countrywide or statewide. We're just talking about ARC student population. Now, obviously, I'm not going to take my measuring stick and go out there and stop everyone, in the parking lot and go like, I want to measure your height because I'm doing this study, right? But I can make an extra credit homework assignment for you guys, right? So before you leave the classroom, let me measure your height, and I will bump up your grade by 0.5%.
Are you for real? I'll take that.
That's hypothetical. Hey, this is a class about hypothetical stuff. So anyway, but I can do that with a class of, let's say, 30 or 40 people. The true population of ARC is about 30. Okay, but I can have my sample of only about 40 people. So with the 40 people, I can get two things. I can get one, the average, which is just adding up all the height divided by the number of people. I get the average for this class. Okay, it is the actual average of these people in this class. I can also get a standard deviation, which is a number. Okay, we'll just call it a number. Okay, so with that. Okay, so let's say this is the actual average. We call it, x mean, okay, the mean of this particular curve. And we also measure the standard deviation. The standard deviation, SD, or I think it's in lowercase sigma, is standard deviation. And that's also, computed by looking at the actual heights of this entire class. So now the question is, where is the actual mean for the campus? Because I'm not really interested in the average of this class. I want to know on this campus what is the average height. So that's the question. Okay, what is the chances of the actual population height is somewhere here, as opposed to somewhere here or here? That is why statistics is important. Okay. It's for you to look at a sample and then make a conclusion about the likeliness of the true mean of the entire population. And then using that, you can do, is it called t-test? Tail test? So you can basically say something like, okay, I suspect let's say the average of this class is 5.8, okay? So, and the standard deviation is 1 inch. Okay, I'm just pulling a number out of thin air. So now the question is it really just the sample size, this particular sample being like completely non-representative of the campus? What is the likelihood of the actual average height of this entire campus is actually 6 foot? Now, 6 foot is 8 inches away from 5.8, which is quote unquote the average of this class. And what did I say about the standard deviation? 1 inch, right? So it's 8 standard deviations away from the measured mean of this sample, which means the probability is really, really small. Okay? Is it possible? Yes. Is it likely? Very, very unlikely. On the other hand, if I say, well, the college average maybe 5.9, okay, is it likely? Yep, it's only 1 standard deviation away, and the chances of something being 1 standard deviation away is actually pretty high. So that's how you can, refute, claims of something by looking at, something that is measured by a sample. So anyway, yep.
Just out of curiosity, how you come up with your standard deviation? Say,
The standard deviation is, if I remember correctly, it is each sample I goes from 1 to n. Let's say we have n people. So it's xi minus the mean of x, and then the whole squared. And then the whole thing divided by, if I remember correctly, it's n minus 1. So that's, the standard deviation is the square root of that. Or something like that. I'm not teaching statistics, but I know it's n minus 1 though.
I think the top half is definitely right.
Okay, the n minus 1 is definitely right too. I just cannot remember whether the n minus 1 is inside the square root or outside. I'm pretty sure it's inside the square root, because outside the square root is called a variance. So the n minus 1 is kind of important because with only 1 sample, you cannot claim to have any standard deviation. There's no way you can actually estimate how the overall population distributes. You need at least 2 samples to have a quote-unquote standard deviation. Cool stuff, actually practical stuff. Why does it relate to computer science? Looks like this is something that only statisticians need to know. So as a computer science person, why do you think you need to know this?
Once you write like a program that collects data, you need to like see the average of the data and stuff like that.
Yep. And also, based on how many observations do you need to make, let's say of hard drive failure or transmission error or stuff like that, before you can say, okay, I think we have data, because the standard deviation is like getting like this small, so I know, whatever I'm measuring is really close to the true actual value. Doing any additional tests is not going to improve the accuracy much. That is why it is useful in computer engineering, because computer science people are always under the impression that things are always perfect. If I transmit a byte, it's always going to be received correctly, right? And then computer engineers or electrical engineers will go like, no, 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 a lot of things can go wrong, and things do not happen in a quote-unquote discrete way that software people like to think about. Yep.
Also, the hard approach, just come up with a bunch of tests for what you wrote or something like that, and then actually proving it. Computer science seems to be more you actually prove it versus one random test.
Yeah, statistics is interesting, but it definitely has applications even in computer science and particularly in computer engineering as well as electrical engineering, because they have to deal with noise issues, signal to noise issues. There's to everything, there's always a signal to noise ratio. Not to the software people, the 0 and 1 people go like, nope, everything is perfect. But when you're the one implementing the hardware, you go like, oh no, everything can go wrong. The only difference is how often does it go wrong. Yep. Standard deviation is over n, not n minus 1?
So it's if it's sample, standard
Yeah.
it's not the entire population, but if it's a sample, it's n minus one. Yeah, sample is
Yeah,
minus one.
this is for the sample, right? Yeah. So it is correct in this context. I mean, yep. Okay, so let's try to solve another problem, but this time it is I'll let you guys decide whether it has to do with binomial distribution or not. Okay? So we are at a casino scenario, and we are looking at coin flips. Okay, coin tosses. Okay. So let's say out of each experiment has 6 trials, which means 6 flips. Okay. And let's say we observe total number of observation is, I'm just pulling a number out of thin air here, 2178. Okay. And then we say that the number of experiments with an outcome of 3 heads, 3 tails. I'm going to make this one easy. 3 head and 3 tail turns out to be, let's call it 900. Okay. So if you just look at these numbers, I'm pretty sure most people will look at this and go like, it's kind of questionable, right? Is the coin loaded or not? Looks kind of loaded to me, okay? Because if the coin is not loaded, 3 head, 3 tail should be 2,178 divided by 2. This is obviously off a little bit, okay? So now the question that I want to ask you, this one is actually too easy. The question I want to ask you is, assuming the coin is loaded, okay? By looking at just these observations, how is it loaded? Okay, so let me write down the question. Okay, assuming the observations are representative. In other words, we are not just observing something that is really unlikely 2,178 times. What are the chances of landing on a head of this loaded coin? Yes, go ahead. Okay.
Is it 6 flips?
Hmm?
Are we looking at like 6 flips for each observation?
Each experiment has 6 trials, okay? So we observe 2,178 experiments, the outcomes of 2,178 experiments, okay? Out of those observations, we counted and go like, oh, okay, if we just focus on 3 head and 3 tail, 900 observations out of 2,178 ends up with 3 heads and 3 tails. So assuming that we are not observing something out of the ordinary, this is actually representative of the behavior of the coin, how loaded is it? Question? Yep.
Yeah. What's confusing for me is that since it's like 3 heads and 3 tails, like it's an even amount of each.
It should be even, but it's not, right?
Well, it's like right. So our expected is it should be like. Actually, I don't know.
Okay, go ahead.
So is it like out of 2,178, 900
Yes.
experiments have a 50-50 chance, but the rest don't?
No, no, that's not. Yep.
Right, that's what I'm throwing out. Okay, but you could use binomial distribution to figure out how many outcomes there should be.
Mm-hmm.
Or yeah, how many outcomes there should be. Yeah.
Okay.
Compare that.
You could. Yep. Mm-hmm. Yep. Go ahead.
And just based on this, is there a way for us to tell which side it's loaded onto? Is it
We cannot.
it's
That is a good question. We cannot tell which side is loaded, but we can tell how it is loaded. Yep.
Or you start with like what is it? The common of 6 trials and 3 heads or 3 tails.
Yep. 6 choose 3 times. Okay, so let's say so I'm going to use head tail, so that's easier, right? So 3 heads and 3 tails. The probability of this should be about the observed probability is 900 divided by 2,178. Okay? So now what are we solving for? We're solving for h and t. So you look at this and go like, oh, that's not possible because we have 2 unknowns and only 1 equation cannot solve for the unknown. But we are forgetting one thing. H and t, they are, one is the 1 minus of the other one. Okay? So that means we can now look at this as the combine of 6, 3, h to the power of 3, 1 minus h to the power of 3, and that equals to 900 divided by 2,178. Now is it solvable? Yep. So, if I ask a question like this, if you get to this point, it's good enough. Okay? Because what I want to know is, do you know what equation you want to use? Do you know this relates to the binomial distribution? That you have to use combination and these particulars, and then use 900 divided by 2,178 as the observed probability, and then you equate these two and say, okay, if these two are equal to each other, then we can figure out what is h and what is t. But it is absolutely true that we cannot really differentiate. Is it loaded on the head side or is it loaded on the tail side? That we cannot tell. Not from just one single observation. If I give you a second observation of 2 head and 4 tails and some other number, then you can solve for that. Is that okay? Yep.
Just curious on the exam, is it fine to just write combin 6-3 or 6 choose 3?
Yeah, but but if you want to, if you're short on time and you want to make it faster, the other notation is actually easier, or just C. So combin is just how we use it in the spreadsheet. But the quick and easy way is n choose m like that. So you use 2. Yeah?
That's just fine to.
Oh, that's fine, because this is the notation that I actually use in my notes. It's only that when I'm using a plain text editor, instead of just using uppercase C and M, which is kind of more confusing, I use combin that spells out this is combination of and choose M. Yep. Very good. Are there any other questions related to discrete probabilities? No other questions? All right. If there are no other questions, we can move. Yeah, go ahead.
So when you say combin 1 minus head, you're thinking about the weight of it?
No, the probability. So h is the probability of landing on a head if you just make one single toss, okay? What are the chances that it will land on a head? That's h. So that means 1 minus h is the chances of landing on a tail. But we can't really differentiate, with only this number. We cannot, really differentiate. Is it tilted on the head side or is it tilted on the tail side? We cannot make that differentiation. Yep.
If it wasn't an even split of 3 heads and 3 tails, let's say if it was 2 heads, 4 tails, would we then be able to
Yes.
get a little bit closer?
Yep. Then you can actually know which way is tilted. Yep. Mm-hmm. Yep.
I noticed a lot of probability problems in the examples that we've had use combinations. Do permutations come up every now and then, or is it not as common? Or?
Permutation comes up when ordering is important. So it does become important in certain cases. It's just that most of the examples that we have looked at, do not involve the use of permutations. The reason why combination is used more often, when in our context, probably has to do with we are actually using the concept of a set more than the concept of a tuple at this point. And that's why permutations, is not important because ordering is not important in a set. Even coin tosses is a problem of a set, not a problem of a tuple. Because we are looking at head tail head versus head head tail as the same group in the same event. So that's why ordering is not important in that case. All right. So are we feeling okay so far with discrete probabilities? What about those lotto stuff? You guys feeling comfortable with the lotto stuff? No? Okay, so let's take a look at those questions. Okay, so so we'll simplify the problem a little bit. Okay, so we'll have let's say 6 numbers are drawn from a basket of 36 numbers. Okay, so we imagine that there are 36 numbers, cards, okay, whatever, in the basket. They're all unique, okay, they're all different, and somebody is going to pick 6 of those without replacement. Okay, so let me emphasize. So you don't put a number back before you pick the second number. Whatever you take out is no longer available in the later trials. Okay. So now the question is, what are the chances that someone guesses, I'm going to say 4 numbers correctly, exactly 4 numbers. Okay. Out of the 6 drawn numbers. Okay. So how would you approach this problem? So the first question is, well, is ordering important? What do you think? Does it look like ordering is important to you? Nope, ordering is not important, so immediately it points to combinations, right? Okay. So how can you choose 4? Okay, I just used the wrong word, dang it. Okay, so how do you choose 4 of the 6 numbers that are actually drawn? Okay, I just spoke the answer myself, right? It's 6 choose 4. Okay, very good. Okay, so combin 6 4 is the number of ways to choose 4 of the 6 drawn numbers. Okay, so now the question is a little bit more confusing. What if the other person has to guess exactly 6 numbers? Okay. So now the question is, it's not clear from this question, right? From this question, I didn't say the other person has to guess exactly 6 numbers, of which 4 has to match the actual 4 numbers that were drawn. Okay. So now I'm going to attach that here. Okay. Okay, the rule is the person has to pick 6 numbers. Okay. So in other words, let's say I'm hiding in my office. I have a box of 36 numbers. I drew 6 numbers out of that box without replacement. So in my pocket, I got 6 numbers. Okay. So I come to the class and I go like, okay, your grade now depends on, okay, you just randomly pick, 6 numbers out of 36, okay, you put it on a little sheet of paper, and your grade now depends on, how many of those numbers that you pick out of the 6 numbers that you pick match the numbers in my pocket. Okay? So suddenly you have an interest in knowing the answer to this question. Now this is still correct, okay? Combin 6, 4 is still the number of ways to choose 4 out of the drawn numbers. But your chances of getting, exactly 4 out of 6 also depends on what about the numbers that is still left in my office. Because, I'm interested in 4 of the numbers that you write down on the piece of paper match the numbers in my pocket. But what about those 2 other numbers that you have? Those are going to match the numbers that are still in my office, that is still in the box. Is that making any sense? So now you suddenly have combin. This is good. It improves your chances of actually guessing 4 out of the 6 numbers correctly. So the combin 32. 30 is the numbers that are left in my office. Out of those 30 numbers that are still in a box, 2 of your numbers on the piece of paper that you turn in will match those 30 numbers. So that's why it's a 30 choose 2. Okay? So this is the number of ways to choose 2 of the 30 undrawn numbers. Is that okay? So we have a certain number of ways to get 4 out of the 6 drawn numbers. We have another way to choose the 2 of the undrawn numbers. And when you multiply these two, it will give you the total number of ways to choose to get only 4 numbers correct. Okay, so combin 6, 4 times combin 32 is the total number of choosing 4 out of 6 drawn numbers. When asked to guess exactly 6 numbers. Okay, so I think that, does that make it clear? Is that okay? That's not a probability. This is a pretty big number. A probability is always between 0 and 1. So that means I have to look at this product, combin 6, 4 times combin 32. I have to look at this product divided by something to get to the probability. So if I say, hypothetically, I have to emphasize that if this is what you can achieve, you get a B out of this class. Okay? So my question now is, what are the chances of you getting a B if this is how you get a B out of this class? Yep.
About the common 32 part,
Uh-huh.
where it says the number of ways to choose 2 of the 30 undrawn numbers.
Yes.
Why do you want to choose 2 of the 30
Okay, so let me see if I can kind of present this graphically. So the problem is, like, this is why the mic is nice, because I think it's still recording at full volume, whereas before when I had that stationary mic, there'll be nothing left, right? Because the AC is on, it's too noisy. Okay, so the question is like this. So the game, or the way you get your grade, okay, is you write down 6 numbers. You're guessing 6 numbers that I drew from my office, okay? And so this is your side, this is my side. So on my side, I pick 6 numbers, 1, 2, 3, 4, 5, 6. These are the 6 numbers that I have drawn out of the basket. And then I have 30 numbers, 30 of these that are still left in the basket. Is that okay? So to get a B out of this class, according to this hypothetical scenario, is exactly 4 of these numbers would match 4 of these 6 numbers. What about these other 2 numbers? They're going to match 2 of these 30, right? So that's why the total number of ways that you can guess 4 out of 6 correctly, but have the other 2 wrong, not matching one of the 6 numbers that I have drawn, is the product of combin 6, 4 times combine 32. Okay? But now the biggest question is, what is the probability? So the probability is basically the ratio. So the ratio is over the entire omega. The entire omega is basically saying how many ways can tag choose 6 numbers out of 36. Once again, I just told you about the answer. Right? 36 choose 6. Okay, so that's the total number of combination. So now the probability is combine 64 times combine 32 divided by combine 36. Okay so far? Is it making any sense? It's good? Okay. And I hope you guys still remember the birthday question. You know, what are the likelihood of not having anyone in the class having the same birthday? And that chance, drops really fast when the number of people in class increases. Okay, cool. All right, so unless you guys have more specific questions about discrete probability, I'm going to move on. Yes?
Sorry about this, but
No, no, go ahead.
since what's it called? You choose 4 out of 6, and you will probably get 4 right. And how, why do you exclude the other 2 from the?
Because I'm just saying that what are the chances that you guess 4 out of the 6 numbers correctly?
That's just the way the question was worded. He was just asking if what would it be for.
Because you might have thought of that 32 in your pocket, for example. Because you had 6 numbers out of 30.
I only have 6 numbers in my pocket because I chose those 6 numbers from a box, right? So I have 6 numbers in my pocket and 30 numbers still in the box in my office, in my cubicle. Those are not the chosen numbers.
I wasn't seeing the full picture. That's probably why. Because after you divide by the combine 36 or 6, you can actually see that probability.
Yep. Okay, then you had a question? Yep.
I just think that the ambiguity there is that because you have to get exactly 4 numbers, you make the assumption that the other 2 you chose was wrong.
Yes.
So I think the other people are thinking you can choose 4, but maybe you can get 1 or 2 right. But
Oh, okay.
so it's like
No. Okay. You okay? I
so you
see.
have to get exactly 4, and
Yep.
the other 2 won't be.
Okay, thank you for the clarification. So that is actually correct. My intention is you get 4 and exactly 4 correct, and you get 2 wrong, basically. So you pick 6 numbers. What are the chances that out of the 6 numbers that you pick, 4 matches the ones that I actually chose out of the box, and then the other 2 do not match any of the numbers that I have drawn out of the box. So I think that's probably the, 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 the the issue that some of you are having because I did not communicate that clearly. Cool. So any other questions? No other questions? All right. So if you guys have any further questions, we can go back to this one. If not, we can. I'm gonna write some more modules like this week because I'm running out of topics. This is one of the first semesters where I have enough time to go over, graph topics, in time. So I'm going to add some more topics later, but don't worry, as far as you're concerned, we are not running out yet, okay? Okay, so we're going to talk about graphs, and then we'll get back to predicate logic and possibly recursion and the complexity of algorithms. So we'll get back to those topics when I have time to kind of retype things. I don't want to teach out of PDFs that I capture from Moodle because I really want to have everything kind of natively and correctly typed. If you don't mind PDFs, I can teach it out of the PDFs, but it's not the way I prefer it. Okay, so let's talk about graphs. The first thing about graphs is why do we need to study graphs and what are they good for? And what exactly is a graph? So to draw a picture I just erased one. Damn. I'm going to redraw that.
Let me draw a graph.
Yep. Okay, so this graph is about how you take classes to complete your computer science degree. But these are only the core classes to computer information science. It does not include calculus or anything like that. So you start with P300. It gives you the prerequisite to get enrolled in P360. Once you have taken P360, you have two ways to proceed. You can take P400, and you can also take P310 at the same time. After P400, you can take P430. But because 430 is the co-requisite of this class, 440, so that means you can also take P440 in the same semester. So I'm just going to simplify and not really express the idea of a co-requisite. We'll just say that once you have taken 400, you can take both of these classes for simplicity. This is a graph. Now, it is also a tree, but every tree is a graph. So with a graph, you have what we call vertices. This is a vertex, 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 this is a vertex. What connect the vertices are edges. So this is an edge, two more edges, and then two more edges. So out of this particular graph, we have 1, 2, 3, 4, 5, 6. We have 6 vertices, and then we have 1, 2, 3, 4, 5 edges. Is that okay? Yep.
One more time.
An edge is basically an arrow in this case.
Oh, okay.
So you will have to kind of write this down because I'm not capturing that with my tablet. Is that okay? Why is this useful? Hmm? So the overall education path is going to be small and simple like this, right? You have your calculus stuff, and some of these classes may have your calculus prerequisite and whatnot. Yep.
Looks kind of like a binary search tree.
It is not a binary search tree because a binary search tree has one special property: the left versus the right. You have to follow the order. The node itself, the root, versus the left and the right node. There's a specific order that you have to follow. This is not using that ordering. This is basically just an ordering based on prerequisites in this case. And it may not be binary. This one is binary in terms of what it looks like, but you can have a single class that can be the prerequisite of like 3 other different classes, right? It's just that I don't have an example like this for the computer information science degree. Is that okay? All right. So I'm going to pop up here. Yep.
Well, 360 can also allow you to take 401, which is Java, right? That could be a scenario where you have
Right.
one.
But 401 is not in our transfer degree, so I'm not showing it. But if you want to show it, yes. So you can say P401 is over here, which is Java. And then you can have a P3, not 60, what is Visual Basic? 370. So P370 can get to 360. There we go. Okay, so we can make the graph more complicated. But one thing is kind of important. These edges are directed. In other words, they start with a particular node or vertex. They end with a particular vertex. It's only in one direction, not in the opposite direction. Okay?
So your vertices and edges would change with the addition of the 370 forward, right?
Say that one more time.
Your vertices would change from 6 to 8 with the addition of the 370.
Right, so with these, I would have 8 vertices and 7 edges.
Okay.
Yep. Mm-hmm.
Just double check.
Yep. And it's not a tree anymore. It's not a tree anymore because there are 2 vertices going to one single vertex. Yep. Mm-hmm.
Using this tree, can you possibly calculate like how long it will take you to finish? Kind of like saying like one edge.
Yep.
This period of time, and then somehow.
Yep. So if you do a breadth first search, the number of levels that you need to perform to do a breadth first search will tell you the number of semesters theoretically that you will need to basically take all the classes. Okay. So here's one application. Now, when you look at this, it's not very complicated, but when you look at all the classes you have to take, including all your GE classes, all the math requirement for the major, the physics class that you have to take. You guys have to take physics, right, for your computer science degree?
Uh,
Well, you can take
you can take
or
it.
you can take Calc 3.
Oh.
I chose physics plus.
Okay, so you have options, but you can represent the options too, using like multiple branches.
Depends on what school you want to transfer to.
Okay, but here's the fun part. So the fun part is, um, okay, what if you can associate a cost to these edges? Now this one is not a whole lot of fun because the majority of this is a tree, which means you don't have an option. The only part you have an option is here. So if you say that 370 is an easier class and it will better prepare you for 360 than P300. Let's say that's hypothetically speaking, right? Then this is going to be a lower cost alternative compared to this one. Okay? So that leads us to optimization problems. So when you talk about optimization problems, I can show a map, but the Sacramento is not as much fun or interesting as some other places. So I'm going to use San Francisco. Okay, and particularly we'll look at downtown San Francisco. And what do you see over here? Okay, let me hide this part here. Get rid of this and magnify this a little bit more. Okay. So what do you notice about the smaller streets? I know it's kind of washed out a little bit, but you can still see it. There are a lot of one-way streets. Okay, so with all the one-way streets, that means these directed edges become particularly important because you cannot go backwards. Okay, so let me see if I can pick out a particular example here. So let's say you want to go from here, this particular intersection, to this particular intersection here. So you can go through Turk, make a right turn, and get there, right? You can also make a right turn right away, and then get down on Willow, and then get to this place. But not every single crossing has a traffic light. So you may not be able to cross. Some may have traffic lights, some may not have traffic lights. And then depending on the traffic pattern, with the ones without traffic light, you may not get a chance to go across, ever. Okay? So that makes directed edges particularly important. Now, you think of, okay, how many people watch, what is the name of that show? Mythbusters. Okay? Do you guys remember they did one episode on Mythbusters in San Francisco? And the question, right-hand turns, exactly. So the question is, are right-hand turns less expensive than making a left turn? Okay. So the question is, so let's say you're at an intersection like this. Okay, this pen is out of ink. Okay, so you're at an intersection like this, and you are in this direction on the right lane. Okay, well, not right lane, but you're heading in the to the north direction. So the question is, if you have a block here, is it less expensive? Nope, I'll take it back. Is it less expensive to go through this block to get to this direction, or is it less expensive to wait for a left turn to go to that same direction?
Are they all one-way streets?
Let's assume they are not necessarily one-way streets.
They are not?
Yeah.
Okay, then that would make a difference. Because if they were all one-way streets, then left is
Thank you.
the same as a right. If
I don't understand why they would blow leaves and do that kind of thing today, like at 1 o'clock. Okay, so as they found out that the answer depends on what you're driving. If you're driving a regular passenger car, especially if you're driving a Prius, making a left turn right away is less expensive because when your car is stopped at a traffic light, it doesn't burn any gas. It just stops everything, okay? So you just wait. it depends on how you classify cost, right? But if you're driving one of those big diesel delivery trucks, they found out that actually making right turns was less expensive because idling is actually not any less expensive compared to traveling, and it takes longer before you can make a left turn, as opposed to right turn, right turn, right turn. It's predictable, and as it turns out, the right turn method works better compared to the left turn method when you're driving a delivery truck. But if you're driving a Prius, probably it's not the case because if you're just looking at the consumption of fuel, a Prius doesn't use any fuel when you're just waiting. Yep.
Doesn't your car also burn more gas when it's accelerating?
Oh, it heats up, yeah.
I think diesel cars are very different compared to gasoline cars because they have tons of torque, but no horsepower. So they are not the same. So when they idle, consuming a lot of fuel as well.
So now there's like a huge variance as far as
Yes,
acceleration.
but they found out, empirically, they found that the right-hand turn was actually less expensive
For
for delivery trucks.
oh, for delivery.
For delivery trucks, they tried it with a sedan and was not less expensive. Yep.
As far as the acceleration versus idling kind of thing, diesel trucks idle burning far less fuel than the equivalent sized gasoline engine
They do. Okay.
because they're not required to keep resist air going in, so they're on lean
Oh,
all the time. It's always lean. There's never a rich condition for them.
I
So
see.
they can really like sit the fuel at idle,
Mm-hmm.
but they're also really heavy. So if you have a loaded truck, trying to stop that, you're
Mm-hmm.
losing all that energy in the brakes.
Right,
And
right.
then re-accelerating again, you're burning a bunch of fuel, which would be your left turn condition.
Okay.
Whereas if you can maintain even a little bit of your momentum, making right turns the entire time,
Uh-huh.
because you didn't have to stop in theory, that's conserved energy.
Okay.
It's always possible.
But the point. Okay. So
On
that's interesting because they found out that the right turns were actually less expensive, which was surprising to me too. Yep.
And is that considering that right turns in the case that you wouldn't stop all the way for a right turn, that you could continuously, like you said,
No, I think
take some
it is empirical. They just did a few runs and figure out the actual statistics.
and if you got a green light,
Mm-hmm.
you can still have your left turn as a red light while floating the
Yep.
green light constraint, right?
Yep.
Yeah.
But remember, in San Francisco, there are always pedestrians. Constant stream of pedestrians. Yep. What about going in the opposite direction? Well, as it turns out, it's possible. It's just extremely costly. So, but this is the reason why. This is why it is related. Okay, the prerequisite chart that shows you okay, you have to take this class first and then take that class, can use a graph representation, but a map can also use a graph representation. So the way you turn a map into a graph representation is at every single point that you can make a decision, it becomes a vertex. Okay, here's a vertex. Here's another vertex. Okay, if you get side streets, every single time you have a way, you can make a decision, it becomes a vertex. An edge is now connecting from one vertex to another vertex. Once you have made a choice, you have to go to the next vertex because you can make another choice. Is that making any sense? But because of the way that San Francisco is laid out, there are so many one-way streets, especially in this part of the town, it has to be a directed graph. In other words, the edges have to be directed. In other words, you can only go from here to here in this direction. But what if I'm here and I want to get back to here? You have to go around the block. Now you can choose between go around the block in one single block or in two blocks. Okay, why would I choose to go around in two blocks instead of one? Because this can be a lot more congested than the other one. So there are times when you go like going a further distance actually makes more sense, or it saves you time in San Francisco than going for the quote unquote shortest route. If you want to reduce the time traveled, it actually might make sense to go a little bit further, go around something and then back.
To witnessing it. I remember when I did a job down there, I went to go to Japantown. I darn car.
Well, in San Francisco, one of the things that you have to factor in, if you're not delivering stuff, okay, is can you find a place to park? So that is difficult to take into consideration because then it becomes probability. And it's not just the probability that we have talked about in this class, because that probability of how many space or the chances of having an empty spot open at a particular time, that's not the probability that we have studied at this point, because it depends on time and depends on a lot of many other factors. Does Google now factor that in? Like, I want to say I want to go to this restaurant, but factor in the amount of time it takes for me to find a parking spot?
Yeah, it does not.
Well, if you want to join Google and you get a job interview, this is one of the things that they might ask you. How can you improve Google Maps? I think you need to include the amount of time to find a parking spot. Given when you need to get to the restaurant, you need to figure out the time for travel, for finding a spot to park, and walk from where you park to the restaurant. So if you can factor in all of those things and be accurate about it, you might have something. But you did not hear that from me. So we're going to conclude today's lecture right here. So next class is Wednesday. That's our second exam. And then on next Monday, we'll go full bore into graph theory. So read ahead of me after the exam so that on next Monday we can start to talk about graph concepts. Yep.
What's the name of this lesson?
Huh?
What's the name of this lesson?
Graph theory.
Not graph theory, but I'll put that in my notes as well.
Okay, let me turn off my record.